Good afternoon and welcome to this last talk of this very interesting week. We have the culmination of a series of talks by Rodolfo Aguilar, who speak about the infinitesimal methods in mixed Hodge theory, which is your work with Professor Griffiths or Mark Green.
Thanks. Thanks for having us. I mean, the topic of this lecture is a little bit different from the topic of the conference, but there could be some open questions that could relate. So I hope I could make the comment. So let me give you the structure of the talk that what I want to give. So first, I want to give a motivation for the use of these so-called infinitesimal methods that are really using the derivative of the period mapping that I introduced on Tuesday. Then I will present some examples and some applications of the so-called infinitesimal variation of Hodge structures. Examples and applications. So this is when you have a pure period map, like the one I introduced, and then you take the derivative. So this is basically something that has to do with families. And so the third part is going to be the mixed counterpart of this. So we will introduce infinitesimal variation of mixed Hodge structures. And I will give some invariants. And I will state something called the Torelli theorem that basically says that you can recover, in this case, a pair from the variation of mixed Hodge structure. So in this part, we only work for a smooth pairs. So you take a smooth projective variety and you remove a smooth divisor. But you can also try to do that when you remove a normal crossing divisor or when you go and approximate a singular fiber. So this could be the relation with singularity theory, but we haven't done that yet. So let me start with one. And let me recall the definition of a Hodge structure. So just to fix the notation, so I will consider V a finite dimensional vector space that I will sometimes use the integral structure that it should come from a lattice. And I will consider this with a decreasing filtration that is called the Hodge structure. Sorry, the Hodge filtration. So this is a Hodge structure of weight n. It satisfies the conditions that Fp with the Fn minus p plus 1 bar is going to be isomorphic for every p. So I'm basically writing in a different way the Hodge decomposition, the classical Hodge decomposition. Why I'm doing that? Because when I define the period domain and I wanted the period map to be holomorphic, I use in this way the filtration, and some properties that I will use later will be encoded in this filtration. So I will be particularly interested in the so-called geometric case. So when we have families of algebraic varieties, let's say smooth. So this is a family of smooth projective varieties. And as I explained on Tuesday, we have associated a period map. and I will denote as that time by t. This goes to d, and we have to make the quotient by some monodromy group. And we can distinguish two cases that look at the geometry of D that already appeared in the lecture of Professor Griffiths. So the first one is the so-called classical case. And this is the case when D is Hermitian symmetric. For example, we have the case of when the fiber of this family that I'm giving you are curves or abelian varieties. Or K3 surfaces. In the second case is the non-classical, that it's whenever D is not Hermitian symmetric, and this is the general case. So the motivation for introducing infinitesimal methods is that Hodge theory works well in the case of curves because you have theta divisor, you have the lattice structure, so you can define invariants with that structure we saw in the talk of Nero, for example, the appearance with the theta divisor. But in higher dimensions or in other cases, this lattice could be difficult to compute. You have also this phenomenon in mirror symmetry when you go to the gamma conjecture, the integral structure is usually more difficult. So Hodge theory was very limited in higher dimensional examples, and the idea of introducing these infinitesimal methods is to define invariants or to prove theorems using only the Hodge filtration, using only the complex information. So forgetting about the integral structure and to define invariants with the complex one that are usually easier to compute. So at least for hypersurfaces in PN or sections of ample divisor, but so these filtrations is usually computable. For a hypersurface. So we usually do that via the Jacobian ring, and from these spaces those maps between them we can recover X generic. So this is the so-called generic Torelli theorem. Yutsutonagi. So one drawback of these methods is that we only obtain usually just generic results. So we cannot study the spatial structure of some varieties, but in general we can say something about an open subset of the module space. So this will be the motivation for introducing infinitesimal invariants. So now let me give you the definition of infinitesimal invariants. So let me take a point B in the base. So we have the derivative of the period mapping let me write it in the following way. So you will take the tangent space at B, and if you take the action on the Hodge filtration, the second point of the theorem that I showed you last time showed that it decreases only the degree of the filtration by 1. So the so-called Griffiths transversality. And so the definition of infinitesimal invariant of Hodge structures is the formalization of the properties of the period map, of the derivative of the period map. So an infinitesimal variation of Hodge structure is going to be a triple with a T, a complex vector space this is playing the role of the tangent space at the base, at a point at the base. So V is a CMT module. So we have an action of the of this vector space on the filtration, and you have equality of mixed partials. So this is going to give you a C module, and then you need to have this decrease in filtration, and we need to add this condition, this transversality condition. So this is what is formalizing the properties of the differential of the period mapping. And so what infinitesimal methods are doing is that essentially a variation of Hodge structure is something very analytical. So when you prove things, you do things by analysis most of the time, or allow minimality more recently. But in this setting, you can use algebra. So you really need to identify the pieces, the graded pieces of this filtration, and you can obtain some consequences for this. So for example, the most simple example is let X be a curve, and in this case, the period map will be you just take the vector space, and it can be seen something as follows. So the transversality condition is decreasing this by 1, and then you are going to, using this symmetric structure, you are going to team square of, and I will use the cohomological description of this. These are the dual of the 1 forms. So whenever you have something like this, you have so every tangent space you are associating a morphism, and you can associate invariants already there by looking at the rank of these maps. So you have determinantal varieties associated already to this infinitesimal variation for curves. And so this will give you invariants that I won't really use. And this will, you can recover already a non-hyperelliptic curve from this variation. So you have the dual map, you can look at the kernel, and this will be simply multiplication. And you can see at in the canonical embedding of the curve, that the kernel will be those quadrics vanishing at this curve. And then you have something called Petri theorem. But you have invariants, and you can recover the non-hyperelliptic curve of this infinitesimal structure already. So this is example 1. Let me go to example 2. So this time for surfaces. So you have the filtration, and you have the SIMT module structure on V. So we can associate, let M be the graded pieces of V with respect to F. And this is a finite dimensional SIMT module. And you have associated to these possible groups. So what is this doing? This, I will just apply 2 times the period map. I will iterate this structure, and I will obtain something like this. So if you have FP and you apply this derivative, you will go to omega 1 of x of f p minus 1, and then you iterate. And you can filter these things. You have an increasing filtration, sorry, a decreasing filtration. And you can filter also this, and you will have some groups associated to that. So what are the type of results that you can obtain from this? You can obtain a result for surfaces as follows. So the following theorem is due to Green and Poisson. So let me denote by MD2 to be the smooth surfaces on P3 of degree D. X smooth of degree D. And inside this space, I will have those surfaces that have a bigger Picard rank, bigger than or equal to 2. This is going to be called the Natter-Lefschetz locus. So these are the surfaces such that the rank of the Picard group of X is going to be bigger or equal to 2. So it was known as the theorem of Natter-Lefschetz that every curve in a general surface of this is a complete intersection. And so by using this kind of methods and this kind of groups, you can prove an explicit result. So then for D bigger or equal to 4, the codimension of this Natter-Lefschetz locus is bigger or equal to D minus 1. And you have equality if and only if X contains a line. So this has been recently generalized by Baldi, Klingler, Ulmo to hypersurface in higher PN. This also can be seen as using infinitesimal methods. Any question? So let me give you a last example. So when you have a Hodge structure, the f of odd weight 2p minus 1, we can associate a compact complex torus in the following way. So you need to quotient by the Fp part of the Hodge filtration, and then you quotient also by the integral lattice. And this is going to give you a compact complex torus. So most of the time it's not an abelian variety. In the geometric case, you have that v is going to be equal to h2p minus 1 of x. So this appeared in the talk of Ludmilla in the morning, mentioned in the work of Griffiths and Clements to prove the non-rationality of the cubic threefold. And when you have for z inside x a codimension p cycle such that it vanishes on integral cohomology in codimension of p, we can associate a map called the Adel-Jacobi map that goes from cycles with this condition, and the image lives in this compact complex torus. And now this is all for a fixed x, but infinitesimal variations or variations itself consist of this, of a family. So we need to let x and z vary in a base. So this defines something called a normal function. So I won't give the precise definition, but basically when you have a base where x is varying, you have associated a family of intermediate Jacobians. And so if you have also a cycle that is varying in this family with this property, for each point of the base, you can associate a section of this complex torus, and that's, let's say by definition, a normal function. No. And so there is an infinitesimal invariant let me denote it by delta nu. In the first cohomology of the following complex, that is basically the same complex that I brought before, the Koszul complex. So you have Fp of v, then you use the Gaussman connection to go to Fp minus 1, change notation, and use T star this time. You differentiate once again, and you go to Fp minus 2, so which 2. And then, for example, one can show that this infinitesimal invariant is 0 if and only if this section is torsion. So you have a section of complex torus. You have the group structure there, and you can show that this infinitesimal invariant is 0 if and only is this torsion. So when you define invariance, you usually want to see what's the difference between invariance with less structure, let's say topological invariance, and more structure analytical invariance or algebraic invariance. So one of the applications of this is that you have something that is homologous to 0. You can also define a cycle to be algebraically equivalent to 0. And this type of invariance will help you to decide if something is algebraically equivalent to 0 or not. So let me mention the following theorem, due originally to Ceresa and proven by infinitesimal methods by Colino and Pirola. Goes as follows. So you consider C a smooth projective curve of genus G, and let's take B. So I'm going to define a torus like this. This is going to be the primitive part of the cohomology H to G minus 3 of the Jacobian of the curve. So let me finish the statement and then I will explain a little bit more. So in this case, the classical Abel-Jacobi map will give you a morphism of C to the Jacobian. And then in the Jacobian, you have an involution. So C is going to denote the image of the Abel-Jacobi C plus, and C minus is the involution of the Jacobian applied to this. And so this is an algebraic one cycle in the Jacobian of the curve. So this is called the Ceresa cycle. And then this is homologous to 0. So you can define the Abel-Jacobi of this map. In this case, this is going to be in the intermediate Jacobian defined by this V, C plus minus C minus. So this is going to be well defined. And generically, this infinitesimal invariant is non-zero. So this implies that this cycle is not algebraically equivalent to 0, even if it's homologically equivalent to 0. So you have more information in the algebraic setting. So this will finish the second part. Let me stop for a second to see if you have questions. So once again, these infinitesimal invariants are meant to be used to obtain geometric consequences, just like we are seeing here the difference between algebraically equivalent to 0, even if I haven't defined that. And homologous to 0. For example, in the second example, you could see some structure, some varieties of the moduli space of surfaces of degree d. And so the idea is to generalize this. So this all was well known. We wanted to generalize this to the mixed case. So we have seen some work on pairs recently. So we wanted to see what could be done in the pair case, and that was the motivation to introduce mixed infinitesimal methods. So let me give you the definition of mixed Hodge structure. So let me just note it like that. Mixed Hodge structure is a triple finite dimensional vector space D, again with the integral structure. This time you will have also an increasing filtration. F as before is a decreasing filtration. Let me denote it by this. WK goes inside WK plus 1. FP goes inside FP minus 1. And when you take the graded parts with respect with the weight filtration, you take a Hodge structure of the correct weight. So the graded piece of V with respect to W, you intersect the Hodge filtration. Let me have this notation and forget V here. So this is the Hodge structure of weight K. Of course, if you haven't seen this, this is just a bunch of algebra that is telling you nothing. But the geometric idea is that the linear proof that when you have a smooth quasi-projective variety, you can have a generalization of a Hodge structure, and then it also proves that even for singular varieties, you can have such a structure, but we are going to be using here only the smooth quasi-projective case, even when the divisor, let's say at infinity, is smooth. And if you see this definition is you have an extra structure, and when you make the restriction to the graded piece, the successive quotients, you have a null Hodge structure. So the definition of an infinitesimal variation of mixed Hodge structure is going to be very similar. So you have the information as before, you put the weight filtration, and then you require that the quotient is going to be a classical infinitesimal variation. So a infinitesimal variation of mixed Hodge structure is we have 4 total here. Just as before, we add the thing that is representing the tangent space at the base, and T is a complex vector space. B is a sigma T module. W is an increasing filtration. F, a decreasing filtration. And they have to satisfy also Griffiths transversality that I wrote like this for the pure case. the tangent space that acts on Fe goes to Fe minus 1, and it doesn't modify the weight, and when you take the graded pieces, you induce an infinitesimal variation of Hodge structure. So once again, I'm just writing the definition for completeness. The idea is always to use the geometric case to obtain information about the problem that you are working geometrically. And so the idea is that before we want to define invariants, so that we can say something about the geometry, and the first thing is that we can define something generalizing the infinitesimal invariant for normal functions. This is as follows. So given A and C Hodge structures of weight, let's say K and K plus 1, we have a mixed Hodge structure of length 2 that is given by extensions of this. So you have A that goes to B, goes to C, and goes to 0. And this really reflects the geometric case when you have X that is smooth projective, and Y is also inside smooth projective. So you have this type of weights. So when you have this type of weights, these extensions are classified by an element of the following group. So you have an extension in the extension class of mixed Hodge structures from C to A. And Carlson proved that we have a formula as follows. So you need to look at the homomorphisms from C to A, and then you need to quotient by those homomorphisms that doesn't change the Hodge filtration. And then you need to quotient also by the integral structure. So this is very similar to the intermediate Jacobian that we have seen. You quotient by something in some part of the filtration, and then you quotient by the integral structure. And now we will suppose that we vary this extension class in a family. We want to define an invariant of this, and we will mimic the definition of the infinitesimal invariants of normal functions. So vary this extension class in a base and define so we can also take delta E to be the image of E by when we vary, we have a connection in the base induced by the variation of each of the parts. In the first cohomology group, of the following complex, and once again is something like the Cauchy complex. So you take F0 of V, and you take this Gauss-Manin connection. We once again have Griffiths transversality in this mixed case. So it decreases the Hodge filtration just by 1. And we apply once again nabla. We decrease this by 2. V in this case is the homomorphism. So the tangent space at this is just this part. It's a compact, in this case, compact complex torus. So we are defining an invariant that is given by the differential of the extension class. So for those that like the generations, it has been there is some work like this. You can define the derivative of the period map in the degeneration for certain classes. And this is also generalizing that. This is done by Friedman, special cases, I think K3. But we are doing it in this specific case. So as a first example of this, I'm going to write that when you take very special C, you obtain the previous infinitesimal invariants of normal functions. So let X be a smooth projective variety, and set inside X a codimension P cycle, once again as before, with the cohomology class equals to 0 in H2P of X with integer coefficients. So then we have also a short exact sequence like this in cohomology given by the complement of this that I'm not going to write, and the extension class in this Hodge structure. Let me write like this. It's actually the Abel-Jacobi map of Abel-Jacobi map of this cycle. So if we vary X and Z as before, we obtain that this infinitesimal invariant is actually the same as the infinitesimal invariant of normal functions that we have introduced before. So I would say that this invariant is in general mysterious. We don't really have a full interpretation of this. This is a first interpretation that if you consider the case where of normal functions, it gives the same invariant as before. And we also have another interpretation in a special case of threefolds, and actually most of the part we work for threefolds, and more specific for the cubic threefold and a K3 inside the cubic threefold. But in this case, let me just take X at threefold. Once again, smooth projective. And let's take Y as surface. So again, smooth projective. So what we are actually looking is, given a variable embedding f from y to x, we have a graph of this embedding in the product of the, and we can show that this infinitesimal invariant after some small modification, a small quotient, is going to give you the derivative of the Abel-Jacobi map for the graph. So what are we doing here? If you have a pair of varieties x and y that are fixed, they don't vary in moduli, we are getting an invariant of something keeping these two things fixed. So the only thing that can vary is the embedding. So in this case, we can show that this invariant is related to the problem on how to embed a smooth, in this case, surface inside a threefold without changing the complex structures on Y. So it's a measure of in how many ways you can embed a given surface inside a complex threefold. So this is one of the few cases where we have a geometric interpretation of this. This is given just by computing explicitly the derivative of the Abel-Jacobi that is known, and in this case the delta invariant of them. So let me state a theorem that was probably known for experts, and this is as follows. So this is the general case. Consider x and y to be a smooth anticanonical pair. So I mean, this is smooth projective, this is a smooth projective, and it's in the linear system of minus kx, and then we can prove the infinitesimal Torelli. So this will tell you that if you consider the universal family of the formation of the pair, the differential of the period mapping is injected. This is the tangent space. So the deformations of pairs. So we have seen something similar in the lecture. Most structures. And the proof is really following the same idea as the complex projective Calabi-Yau smooth. So you use the volume form to induce an isomorphism between the tangent space and some power of the forms with, in this case, with logarithmic poles. And then you need to identify the vector spaces. So we have also another invariant that we call the cubic form. So this is another thing that could touch mirror symmetry or singularity. In the Calabi-Yau case, you have something, a cubic form called the Yukawa coupling. In this case, we also have a cubic form. I'm not sure if there is anything known in the mirror symmetry for log Calabi-Yau. And this form has appeared before in work of Markusevich. Let me try to describe it briefly. So let X be, in this case, a smooth projective Fano threefold. And we have a map given if you take a section of its anticanonical divisor, and then you take a one cohomology class in of omega 2, then you just use coproduct, and this goes to H1 of Tx. But if you use the period map goes as follows. Using the quality of partials. Let me omit some computations. You have a map like this. So basically, we can form a cubic from two ingredients. One is the period map, and the other one is using a smooth section of the anticanonical divisor. And then together, I need to dualize a little bit here. We have a map like this. H0 minus K of X. This is going to be S3 of H1 omega X to dual. And then a first theorem that we can prove for this cubic in the cubic threefold case is that this cubic is generically smooth. So theorem, let X be a cubic threefold. And Y anticanonical section. Then for generic pairs X and Y, the cubic, let me call this two stars. The cubic given by double star is smooth. So we are not aware of something similar about studying this cubic in the Kawa coupling case, probably the case, but it's why do we restrict with the cubic threefold? Because we can use the Jacobian and we can have more explicit formulas for everything. And so let me just conclude with the generic Torelli theorem, and I can make more comments. Generic Torelli for pairs that says the following. So let X, Y be a smooth anti-canonical pair with X the cubic threefold. And then X, Y is genetically determined by the mixed Hodge structure on the complement. So what do we use to prove this? First, we use the infinitesimal Torelli theorem. It says that the differential of the period map is injective on this deformation space. So we can look only at the deformation space, and this deformation space has two projections to the deformation space of X and the deformation space of Y. We can look at the kernel of this, and we can express all these groups in terms of the Jacobian, basically. So one important ingredient here is that we can use the cubic in this generic case to relate the equations of X and the equations of Y, and this will allow us to reconstruct the equations for X and Y modulo the action of the automorphisms of Pn. So let me stop here.